So we've discussed how chemical reactions either absorb heat or lose heat. And what we want to discuss now is how can we actually quantify that? How can we actually measure the amount of heat that a system either gains if it's an endothermic process or the system loses if it's an exothermic process? How do we actually do that in a lab? I mean, if you think about it, let's say you have a chemical reaction going where you have some wood burning, okay, like right down here. In all honesty, what we really care about is how much heat are we going to get when this wood burns? Or if you think about it in a car, how much heat, how much energy can we get from burning of gasoline? Those are the actual measurements that make the most sense to us and that we want to know the answers to in our daily lives. So in order to measure the amount of heat transferred, either that the system gains or the system loses, we use this quantity called enthalpy. Enthalpy. And enthalpy is abbreviated with a capital H. We're not going to get into the thermodynamics of where enthalpy comes from in this course, but what we need to know is enthalpy is a way for us to measure the amount of heat a system gains or loses, and it's abbreviated with a capital H. Okay? I know that's a little confusing, but if you think of it, it's kind of representing the amount of heat that's transferred. So it's kind of a way to remember the capital H, but just be careful because in equations, Q, the lowercase q actually represents heat, as we'll see later this week. Now the challenging part is we don't necessarily care about how much enthalpy or heat a substance has by itself. What we care about is how much the heat is changing over the course of a reaction. So whenever we're measuring enthalpies, we're going to be talking about what's called delta H. The change in enthalpy. Remember, delta, this Greek letter, means change. So anytime we put that in front of value, we're talking about how much that value is changing by. So a little refresher, that essentially represents the heat of the product, or our final conditions, minus the heat or enthalpy of our reactants, our initial conditions. Okay. So again, we're going to be talking about delta H, the change in enthalpy of different molecules. How much the system either gains or loses. Well, how can we apply that to what we know already? We talked about endothermic versus exothermic reactions. So here's two diagrams below. How can we now apply this to what we learned already? Well, here, for example, in this reaction on the left, our reactants are starting with a certain amount of energy. And as we can tell, our products have more energy than they did initially. So let's say this is H of our products, our enthalpy of our products. This is H of our reactants. We know H of products here is greater than H of reactants. So if we wanted to figure out the enthalpy of this reaction, delta H, we know it's going to be, as we said before, the enthalpy of the products minus the enthalpy of the reactants, whatever you end with minus what you start with. If this number is bigger than that number, then we know that delta H is going to be greater than 0. The change in enthalpy is going to be a positive number. How does that connect to what we said earlier? Well, we said yesterday that based on a diagram like this would be endothermic, which means the system is gaining heat. Is that supported by the quantitative measurement of enthalpy? Yes. The change in enthalpy is greater than 0, which means that this reaction must be gaining some heat from its surroundings. On the other hand, if we look at this reaction over on the right side, here we have our reactants with a certain amount of energy, H reactants. And here we have our products with a certain amount of energy. So if we calculated the enthalpy here, remember, it's the change in enthalpy would be the enthalpy of products minus reactants. But now we notice that this number is bigger. So let's just make up a number to prove this to us. Let's call this 10 and call this 5. So if you do 5 minus 10, we're going to get a negative number. So what we can see is that delta H, in this case, based on this diagram, is less than 0. Well, does that support what we learned already? Yeah, it does. Because here we learned these diagrams would represent exothermic reactions, which means by definition the system is losing heat to the surroundings. And And is that supported quantitatively? Yeah, the change in enthalpy is less than 0, which means the system now has less energy or heat than it did when it started. That energy is released to the surroundings. So what we need to be able to do is if you see diagrams like this, you need to recognize that this is delta H is greater than 0, which is endothermic. Here, delta H is less than 0, which is exothermic. This relationship, this just needs to be memorized right away. If it's an endothermic process, is delta H greater or less than 0? If it's exothermic, is delta H greater than or less than 0? That needs to be memorized as quick as possible. But now how do we actually apply this to numbers? How do we actually do problems involving these numbers? Well, the first thing is when we're doing these measurements, these measurements are done through something called calorimetry. And basically, if we break this word down, metry means to measure, and a calor is from calorie, which is a unit of energy. More frequently, we're going to use the units of joules, which will be abbreviated with a J, or kilojoules, which will be abbreviated with a little k and then a capital J. These are the units we'll be talking about when we're measuring the change in enthalpy of certain molecules. We'll do calorimetry labs next week to actually practice this concept, but when the scientists have done all these for us, and they've made a bunch of measurements about the heat of formation for different compounds. So, this is an example table of the standard enthalpies of formation. What you'll first notice is that these are written as delta sub F H with this naught, this little 0 up at the top, kilojoules per mole. What does that mean? Well, let's go back and rewrite it over here. Delta H F naught. Let's break this down. This naught up here, this little circle, means standard conditions. Just like there's standard conditions for gases, which are called STP, there's also standard conditions for doing thermochemistry calculations. And you need to know what those standard conditions are. They're at a pressure of 1 atm, and now they're at a temperature of 298 Kelvin. And the reason for that is this is about 25 degrees Celsius, which is room temperature. So the majority of reactions are conducted at room temperature, so scientists can norm on their data. Whenever you see a little knot up here, anytime in this class, that means standard conditions. The F means formation. Basically the idea of how much enthalpy, how much energy is either gained or released when we're forming this compound. And what's important by that is we have to set a standard for substances that have 0 enthalpy of formation. And so what do you need to know? We need to know that the enthalpy of formation is 0 for molecules in their standard state. What are molecules in their standard state? Well, for metals, it's solids. So examples, Fe, solid. Magnesium, solid. These would all have a delta H of formation equal to 0. Something like Mg2+, that's not in its standard state. This would not have an enthalpy of formation of 0. What are some other examples of molecules in their standard state? All the diatomics, the big 7, the weirdo. H2, N2, O2, and on and on. These all have a delta H of formation of 0. We set that as scientists as our standard, which allows us to make calculations from them. So for example, calculate the enthalpy of formation of rust given the equation below. Well, how do we do that? Well, we learned earlier that delta H of a reaction is equal to H of products minus H of reactants, our final condition minus our initial condition. We can now expand that equation to say the delta H naught of a reaction in standard conditions is going to be equal to the sum, the sigma means sum, of the enthalpy of formations of the products minus the sum of the enthalpy of formations of the reactants. Because a molecule might have more than one reactant or more than one product. So how do we apply that to something like this, where it asks us to calculate the enthalpy of formation of rust, Fe2O3, given the equation below. Oh, I didn't give you the equation. Okay, here's the equation really quick. 4Fe solid plus 3O2 gas produces 2Fe2O3 solid. Well, let's just take this equation here. This is something called Hess's law, which we're going to expand on over the next 2 days. And let's calculate the delta H of the reaction here. So let's think about my products, or what are my products? My only product is Fe2O3, but how many moles of them do I have? I have 2. So I need to say I have 2 moles times the enthalpy of formation of that compound, which, okay, we got to find rust on the table here. Here's rust. Its enthalpy of formation is negative 826, so I plug that in. Do I have any other products? Nope, I don't. So that takes care of this section, this section. Now I got to do the reactant side. So subtract. Let's see, my first reactant is, I have 3 moles of O2. What's the enthalpy of formation of oxygen? Oh, it's in its standard state, so it's actually 0. And now I add up because it's a sigma, I got to add the enthalpies of the other reactants. In this case, it's iron, Fe. Oh, Fe is a solid, it's in its standard state, so it's 4 moles times 0. Boom, so this comes out to 0. So I'm basically left with 2 times negative 826, which gives me negative 1,652 kilojoules per mole. Boom. That is the enthalpy of formation for rust if 4 moles of iron react with 3 moles of oxygen. I could ask follow-up questions like, is this endo or exothermic? So, is this endo or exothermic? Delta H is negative, so therefore it's got to be exothermic. Let's do another problem. Calculate the enthalpy for the reaction below. Well, again, we know delta H naught of a reaction is equal to the sum, it's a bad sigma, delta H of formation of the products minus the sum of delta H naught formation of reactants. So let's plug in some numbers. Well, delta H naught of reaction. What are my products? I have 3 moles of CO2 here. So 3 times the enthalpy of formation of CO2. Go back to the table, find carbon dioxide. Here it is, negative 393.5. Plus 4 moles of H2O gas. Okay, so let's go back to the table, find water vapor. Okay. Actually, excuse me, this should be water liquid. Water liquid. Water liquid, 285.8. Negative 285.8. Okay, now I got to do the same thing for my reactants. Okay. Well, let's think about my reactants. What do I have? I have 1 mole of C3H8. So 1 times C3H8 here, negative 103.85, negative 103.85, plus 5 moles of O2 times the enthalpy of formation of O2. Ooh, I don't see oxygen in the table. Well, that's because it's in standard state, so it's 0. So if we go ahead and do the math, we're going to get negative 1967.5 minus 967.2 plus negative 103.85, and that's what we got there. We go ahead and do the last step. And we get for a final answer, negative 9972.7. Don't worry about sig figs, this would be kilojoules per mole. That's how much enthalpy would be released for this reaction. Excuse me, I made a math error there. It should be negative 2238.6 kilojoules per